Geometric series 11.2. So this is a series of the form n equal 1 to infinity of a number times r to the n minus 1. Okay? So what does this look like? This would be something, something along these lines right here. It would be a. If I plug in 1, I get 1 minus 1 gets me 0, so that first r goes away. Plus, and then a times r plus ar times r again gets me r squared plus a, and then r squared times r again gets me r cubed, and so on and so forth. What's happening here? Each time I'm multiplying by r to get the next term. When I multiply to get the next term, that's geometric. If I add to get the next term, that is arithmetic, and that is different than a geometric. So we are multiplying to get the next term. Another version would be, instead of having an index start at 1, you could start the index at n equal to 0. A times r to the n. This is probably my preferred way to write it. You can write it either way. It doesn't matter. I will be able to figure it out. But this is the same thing. When n equals 0, it's a. When n equals 1, it's ar squared, ar cubed, ar to the 4th, and so on. Okay? Now, these pieces have names. A, think of this as the first term. It's the first term in the sequence. So your A is the first term in the sequence. Okay, it's the first term. For this particular one, n started at 1. For this one, n started at 0. You'll see the difference. Okay? The R is the common ratio. This is what I multiply each term in the sequence by to get the next term, and then when I add all those terms together in the sequence, it becomes a series. The common ratio, not ration, so ratio. So if the common ratio in absolute value is between 0 and 1, okay, then the series n equals 0 to infinity of a to the, and then I have r to the n, is equal to, this adds up, it's a formula, a over 1 minus r. Very powerful formula for you here. We're going to use this formula for the rest of the course. Very important that you get this down. Okay? If I have the absolute value of r greater than or equal to 1, okay, then the series n equals 0 to infinity of a r to the n diverges. So if my common ratio is greater than or equal to 1, then the series will diverge. Okay, the series will diverge. Now, to show you a proof of why this works, okay, to show you a proof of why this works, I have the series n equal 1 to infinity of a r to the n minus 1. We said that was a over 1 minus r, right? You'll see how this is the exact same formula here. The only difference is the index 1. Okay, so if I start at 1, then I have to subtract 1 to make it the same thing. Okay? Now, here's the proof. I look at the nth partial sum. S sub n is a plus ar plus ar squared plus ar to the n minus 1. That's the nth term. Okay, that's the nth term. A sub n is your nth term in there. Okay, a sub n. Now, then what can I do? Then r times s sub n. If I multiply everything by r, what do I get? I get ar plus ar squared, right? You'll see how this lines up. Plus ar cubed, plus all the way out to r to the n, okay? Now, if I subtract the two, if I take these two nth partial sums and I do Sn minus Rsn, what do I get? Well, let me copy and paste this here so I can save some time. You're going to have to rewrite it, unfortunately, but you know what? Life's tough. And then copy this. Okay. Right? What's going to happen whenever I subtract all of these? What am I going to be left with? I'm going to be left with, well, this cancels, these cancel in the dots, we got a lot of killing going on, and then those cancel. And so what do I have left? I have a, and then that negative distributes to everything in here, even this last one, minus a r to the n. Okay? So what does this tell me? S to the n minus r s to the n equals a minus a r to the n. Okay? What can I do here? I can factor out a s sub n here, so I get 1 minus r. And I can factor out an a here, and I get 1 minus r to the n. Okay? So if I divide both sides by 1 minus r, what do I get? I get s sub n, okay? S sub n is equal to this ratio right here. So the limit as n goes to infinity of this s sub n is equal to the limit as n goes to infinity of a number a, right, times 1 minus r to the n over 1 minus r. Okay, the a comes out front, right? So this becomes a, and then 1 minus the limit as n goes to infinity of r to the n over 1 minus r. All right, there's two scenarios here. You think about a function where r is changing, okay? If r is like 2, say you had an r equal to 2, that'd be 2 to the n. As n goes to infinity, what happens to this? It goes to positive infinity, doesn't it? But something interesting that happens is if n is like a half, okay, and I take the limit as n goes to infinity, what's going to happen? No longer will my graph go exponentially up like this. It will actually be an exponential decay like this. It's heading down towards 0. Okay? So, this is equal to a times 1 minus 0 over 1 minus r, as long as r, absolute value of r, is less than 1. Okay? However, if r in absolute value is greater than or equal to 1, then the partial sum, when I take the limit as n goes to infinity, diverges. So those are the two possible answers there. Okay? This simplifies to a over 1 minus r, which is what we were trying to prove. All right, so and that concludes my proof. Right there. All right, so let's work through some geometric problems. See if we can't knock some of these out. Here's an example. Series n equal 1 to infinity of 3 times 1 over a half to the n minus 1. Okay. My formula says, okay, geometric series starting at n, my exponent n minus 1, then it sums to a over 1 minus r, where a is equal to the first term. Okay, it's the first term. What is my first term? So a is the first term. What does n equal to 1 give me? It gives me 3 times 1 half to the 1 minus 1. 3 times 1 half to the 0 is 3. So my first term is 3 divided by 1 minus my common ratio. How do I get my common ratio? Okay. One way to get your common ratio is to divide one term by its previous term. Okay. Or you can look and you can see what is raised to the power of n. That is 1/2. That's my common ratio. R is what I'm multiplying by each time I increase n. Okay, if I increase n by 1, then I'm multiplying by that 1/2 factor. So R here is 1/2. So if this is 1/2, then what is my answer? It's 3 over 1 minus 1/2, which is a half, which equals 6. Very interesting. The series n equal 1 to infinity of 3 times 1/2 to the n minus 1 adds to 6? What? Right? Isn't that crazy? Okay, so if you were having trouble figuring out what R is and you didn't just see it like I did, then you can write out the terms. That first term in our sequence was a 3. The next term, if I had, so that was n equal to 1, n equal to 2, what would it be? It would be 3 times 1/2 to the 2 minus 1, which is 3 times 1/2, which is 3 over 2. Okay, and then you could keep going, but all you need is to divide this term by the one before it. So 3/2 divided by 3. How do I do this? Keep, change, flip. That's 3/2 divided by 3. Change, division, multiplication. Flip the 3 over 1. Cancel the 3's. I get 1/2. So my R is 1/2. So that's another way to get your 1/2 if you're having trouble seeing where the R comes from. All right, pretty cool way to do it. Now let's do something even cooler. We're going to prove that 9, 9, 9, 9 repeating forever and ever is equal to 1. Okay? We're going to prove this, and we're going to prove it using geometric series. So how can I rewrite this number in terms of a geometric? Okay? I want to break it up into pieces. The first piece is going to be 0.9. And I'm going to add the next piece. The next piece, I'm going to make it only with this 9 here. So what does that mean? It's going to be 0.09. Okay? The next piece, I'm going to make it with only this piece here. So that's 0.009. And I'm going to continue this pattern as long as I need to until I get the pattern down. I think that should be enough. All right? What's going on here? How do I get each next term? So the first term is 0.9. So what do I know? I know when I'm dealing with the geometric. So maybe if I start at n equal 1 to go to infinity, I want my first term to be 0.9. So n equal 1 gets me 0.9. N equal 2, I want it to get me 0.09. What do I have to do to 0.9 to make it look like 0.09? I can multiply by something. I can multiply by 1/10. All right? If I multiply by 1/10, all it does is move the decimal over, right? Same thing to get n equal to 3 gives me 0.009. I move the decimal over 2 places, right? So instead of multiplying by 1/10, I got to multiply by 1/100. So this is powers here of 1/10. If I put an n in here, does this get me what I want? If I plug in n equal to 1, I get 0.9 times 1/10 to the 1. That tells me that the first term is 0.09. I want the first term to be 0.9. So I want this to really be 0, so I can just subtract 1 here, and that's going to fix it. So this is what I want, okay? So that's what I'm looking for right there. That's how I figure out what my a sub n term looks like, okay? So now that we have this, we can do geometric. This is a geometric series with a equal to, so when you're writing this out on your test, I'm going to be looking for you to say a equals to, tell me what type of series it is. It's geometric with a equal to, well, what is the first term? The first term is 0.9. Okay, and r equal to, what's the common ratio? How do I get from 0.9 to 0.09? How do I get from 0.09 to 0.009? I multiply by a 10th, 1/10. Okay, guess what? Since absolute value of r equals the absolute value of 1/10, which is less than 1, what do we know if my common ratio is less than 1? That tells me something. That tells me that the series converges to a over 1 minus r, which is the first term, over 1 minus r. And the first term is 0.9 over 1 minus 1/10. So what is this? 0.9 is 9/10. Divided by 1 minus 1/10 is 9/10. So a number divided by itself, that actually equals 1. So we just proved that 0.999999 repeating is equal to 1. Okay, pretty cool, right? Had you started this series with n equals 0, that's perfectly fine. Your first term is still 0.9, so, but then I multiply by 1/10 each time, and so all I have for my exponent is n. and that will get me, these two are equivalent answers here. So either one of those would be acceptable. Okay? Let's try this one. Find the sum of 4 minus 2 plus 1 minus 1/2 plus ... How do we do this? Well, we got to figure out what the nth term is. Okay? So it all depends on where you want to start. Right? What's happening here? What is happening? I'm changing. So say I start, who knows, maybe, n equals 1, n equals 2, n equals 3, okay? N equal 4. Is there a way to map those numbers to get that answer? That's the question we got to figure out. Each term switches from positive to negative, positive to negative. So what do I know? I know that I'm going to have a sign changer. I know I'm going to have a sign changer. So I've got some -1 to the n power. Okay? Now, the first term, that's my a. What is the first term? The first term is 4. So I know a is equal to 4. Okay? What about the common ratio? How do I get the common ratio? I take a term divided by the previous term. So just pick something, doesn't matter. I'm just going to pick these two here. So I'm going to take 1 divided by the -1/2. Okay, so my common ratio is the -1/2 going on here. This is going to account for that sign changer there. Okay? So let's start playing with this, see if we can't figure it out. So we know it's going to have an a, r to the n, or n minus 1, whatever it is. So a is 4, r is -1/2 to the n. Okay, let's see if this works. If I start at n equal 1, what do I get? I get 4 times -1/2 to the 1. This gets me -2. That looks like the second term. So how do I make it not the second term? I can turn this into a 0, or I can turn this into a -1. Whichever one makes you feel better, okay? So if I change this to start at 0 instead, this would be what? It would be 4 times -1/2 to the 0, which is 4, and that's the first term. And then the next term would be -2, and then 1, and then -1/2, and so on, right? So that's what we're looking for there. Now I want to find the sum. Okay? So how do I find the sum? Well, I need to know, okay, it's a geometric. So you write this out, geometric series with a equal to 4. The first term is 4. And r, okay, what is r? R is -1/2. Common ratio is -1/2. I multiply by -1/2 every time. That's why it goes from positive to negative, and then a negative and a negative make a positive. Positive and a negative make a negative. Negative and negative, positive. So that's why it swaps from plus minus. Common ratio -1/2. Since the absolute value of r equals 1/2, and that is less than 1, we know the series n equals 0 to infinity of 4 and -1/2 to the n is equal to converges to a over 1 minus r, which is 4 over 1 minus -1/2 which is equal to 4 over 3 halves, which is, keep change flip, 8 over 3. Okay? So this weird looking series where we're adding and subtracting, adding and subtracting, adding and subtracting all the way out forever and ever, if you did it forever and ever, you would get 8/3. Okay? Pretty crazy, but kind of cool at the same time. All right, let's see here. Let's do this last one relating to geometric series. Okay. I want you to find all values of x that make the series converge. Okay, this is kind of where the class is heading to eventually, all right? We're going to find all x values for which the series converges. So you're given a series n equal 1 to infinity, x over 2 to the n. Now, what do we know? It's a geometric. How do we know it's geometric? Because we have some raised to the n power here. I'm multiplying by some common ratio every time. So it's a geometric series with a equal to, well, what's the first term? It's x over 2 to the n, which is 1 for the first term, okay? And r equal to, well, the common ratio is x over 2. So what does this say? This series converges for absolute value r less than 1. When are we less than 1 here? We're only less than 1 whenever we have x over 2 less than 1, because r is equal to x over 2. Okay? Now, technically, this is implied because of the absolute values. It's going to for sure be greater than or equal to 0. So we can drop that other side here and solve this problem. And so when I do that, I get x over 2 is stuck between 1 and negative 1. If I multiply by 2, I get x is between negative 2 and 2. So what is this telling me? This series converges for x in the interval negative 2 to 2. Okay, if you'd rather write this instead, that's fine. But this symbol here means an element of. Okay, x is an element of, or x is in the interval between negative 2 and 2. This is a set theory. Shorthand notation for you. Okay, guys, so that's going to end the geometric series portion.